In Chapter 6 we'll be looking at circular motion and gravitation. Subtopic 6.1 deals with circular motion and 6.2 will be on gravitation. So we'll start with circular motion. To begin with, we need to look at the concepts of angular displacement and angular velocity. So we'll sort of develop those through this video. Now, fairly obviously, circular motion deals with motion where the object is travelling in a circle. So it's a fairly obvious statement, but just want to make that obvious statement to begin with. So it deals with objects moving in a circular path. And to make, well, as we start to have a look at these concepts, we'll start with a simpler scenario to analyse. So we'll deal with constant speed. So with dealing with constant speed makes the scenario a little bit easier to analyse and the concepts a little bit easier to develop. And we can then take that a step further and look at some situations where the speed is no longer constant. Notice that I'm specifically using the word speed here. I just want to highlight to you that with circular motion, the direction is always going to be changing. Since direction is always changing, it means that the object's velocity won't be constant. So in these scenarios, we need to be very aware that the quantities that we're looking at are about speed, not so much velocity. If we are interested in velocity, that will be an instantaneous measurement, so a point in time where the object is at a specific location. So just to start to develop these ideas a little bit more, let's imagine that this dotted path that I'm drawing here is a circular path around which some object of mass m is travelling. So the circular path is going to have a centre here. The distance that this object is away from that centre will be the radius of the circle. And that distance would be measured to the centre of mass of the object. And so at this point in time, the mass would have a velocity that is in that direction to the left. So just to develop this idea about the velocity not being constant, if the object was then positioned over to the left-hand side of the circle, its velocity would then be down. If it was at the bottom of the circle, the velocity would be to the right, and if it was over this side, the velocity would be up. But you'll notice that in each case the size of that vector is still the same, so the speed is still constant. I should also mention here that this representation that we're looking at, think of it as being looking down on top of an object moving in a circle, so this is a horizontal circle. We'll deal with vertical circles later in video 2. Now, circular motion, there's another quantity that we've seen before that we need to bring back again here, and that's the period. So period is the time taken to complete one full rotation. So in this this example, if we had the object starting in that location at the top of this diagram, the period would be the time that it takes for it to get all the way back around to this original position that it was in, so one full rotation. The distance that it would cover in that time is going to be the circumference of the circle. And hopefully you can remember back to some of your junior maths. That circumference is going to be given by 2 pi r. So that means the speed can be calculated. So the speed is going to be given by v, so note that it's not a vector, we don't have the arrow across the top, being distance, so 2 pi r over the time taken, which is the period t. So this equation we'll come back to a couple of times as we continue to develop these ideas. One last thing to mention here too, though, notice that V and R are directly proportional. So if R is smaller, then V will be slower. So that basically means if we then look at an object that's, we'll just change colour here to highlight the difference. If we had an object that was, say, positioned here, a different object, then it's going to travel a circular path that's a little bit smaller, so the circumference of that circle is going to be smaller, and as a result, the speed that it will be travelling with will be smaller as well. So the velocity of that one at that point to the left, the speed at that point, or the speed the whole way around the circle, will be smaller. In that scenario, both objects are going to have the same period. So they both complete one full rotation in the same time. So they both have the same period. And both of them have moved through the same angle, or the same angular displacement. Sorry, through. My writing is not up to scratch. So both move through the same angular displacement. Now, the term angular displacement here is similar in a way to linear displacement, but slightly different at the same time. So angular displacement is basically the angle swept out during circular motion. Now, the situation that we're dealing with in the case above is 2 pi. Sorry, I should also mention there before I go on to that. So the angle that we're going to be measuring, the units will be radians. So circular motion, we always deal with radians. And that angle above is 2 pi. So we don't have to have 2 pi, we're just using 2 pi because it makes the calculation of the distance easier to deal with. But ultimately the angle that we deal with could vary depending on the scenario that we're looking at. Now I want to make a comparison here between linear velocity and angular velocity. So we don't usually use the word linear, but I'll just put it in brackets here. So linear velocity is the rate of change of displacement it then sort of stands to reason that angular velocity is the rate of change of angular displacement. So the equation that we could write for that would be that the angular displacement angular velocity omega is equal to the rate of change of angular displacement. So omega is equal to delta phi and delta t. Now that's not an equation in the data booklet, but it's just one to keep in the back of your mind. So the symbol omega is the angular velocity, and that's in radians per second. Theta is the angular displacement, in radians, and t is the time in seconds. Now, just want to make a note here as well. these terms of angular velocity and angular displacement, they're not really vectors. They're sort of quasi-vectors. They're in a way they are, in that you can talk about whether it's rotating clockwise or anti-clockwise, but then you'd also have to specify the plane that you're looking at and the direction that you're looking at that plane. So the direction's sort of important, but for the purposes of what we're doing, the direction here is not as important. So we'll use the words velocity and displacement, but you might also see angular speed and angular distance being used interchangeably with angular velocity and angular displacement. Okay, if we now look at angular displacement and angular velocity in a bit more detail, if we go with one period, so keeping it nice and easy, so in one period t, the angular displacement, regardless of the scenario, is always going to be 2 pi. So it's always going to be the case that in one period the displacement is 2 pi. So we can write then that omega is equal to 2 pi, so there's the displacement, divided by the time, t. That then leads us to another way that we can calculate the period by looking at the displacement, the angular displacement 2 pi divided by the angular speed omega. The reason why that's important is that we also have an expression for frequency, f, which is equal to 1 on t. So that then means that instead of writing t, we could write that 1 on f is equal to 2 pi on omega, and we therefore have an expression for omega in terms of the frequency, which would be 2 pi f. Again, not in the data booklet for Unit 6, but just something to keep in mind about the relationship between angular velocity and frequency. In the example above, so going back to that example of those two objects, there are a few quantities that are the same, but there are some that are different. So in the example above, both of those objects had the same angular velocity, but different speeds. And the reason they had different speeds is because they had different radii. But we can link those together, considering that we know that we mentioned earlier that the speed is given by 2 pi r on t, and we just identified that if we scroll back up, we've got this expression here for t being equal to 2 pi on omega. So we could then substitute that in instead, so we'd have 2 pi r over 2 pi over omega. And again, some simple fraction calculations. If we divide by a fraction, we multiply by the reciprocal, so that then becomes 2 pi r multiplied by omega over 2 pi. So the 2 pi's cancel, and what we're left with is then the expression that v is equal to omega r. Now that equation is an important one, so it gives us a relationship between the linear speed and the angular velocity as well. So we can see that they're related simply by the radius of the orbit. And finally, just one last little note. We've already seen that speed is equal to change in distance over time, or the rate of change of distance, and we also know that the angular velocity is the rate of change of angular displacement. We can then substitute both of those in, so we'd have delta s on delta t is equal to delta theta on delta t multiplied by r. So the displacement is equal to angular displacement multiplied by the radius. Now this equation isn't in the data booklet, but it's a good equation to keep in the back of your mind to identify the link between angular displacement and the distance travelled around the circular path.